Bienvenidos a la nueva temporada de Coloquios en el CIMA-DCAO-IFAECI. Hoy tenemos el honor de tener a una visitante para arrancar esta temporada. Nos visita Marie-Christin Juhl. I start doing English. Ella es una estudiante de doctorado en la Universidad de Hamburg y está en estos, ya está en su pasantía acá por 2 meses para trabajar en el grupo Sofía y en oceanografía, que ahora les va a contar lo que está haciendo. Y ella tiene un bachelor en física y una maestría en la física del clima y del océano, también de la Universidad de gracias. Thank you for accepting to give this seminar. The floor is yours.
Yeah, thank you for inviting me and thank you for having me. Welcome everybody and thank you for coming. I don't know, should I accept? There's some.
Yeah, just
yeah. Okay, so I want to present today to you regional gridded altimetry on the Southwestern Atlantic Continental Shelf. I'm a PhD student from TU Munich, from Germany, and I'm showing you some of my recent work that I've done and what I'm doing here. And so this is my content of today. Of course, I have a little bit of a background that I've already heard in the Spanish. I want to give a very short and easy introduction to altimetry, maybe a bit of a motivation. If you're not working with altimetry, work with altimetry. And then it's about gridded altimetry, and then my work, the regional gridded altimetry. I show you the content of the paper that I'm right now, I submitted, and it's right now in review. And then I have some slides on current developments and future challenges. It's like a bit of a comment from me on what else is happening outside of this little study I show you, and I show you what I'm doing right now here, or plan to do. Okay. A little bit of my background. So yeah, I'm from Germany. Actually, I come from an island in the Baltic Sea called Usedom. And since I know like the usual reaction, yes, there are islands in Germany. So education done for today. No, I'm just kidding. And there's also a picture, it's very nice. But I moved a bit around for studying, only in Germany, a bit boring. But I did a bachelor in physics at the University of Heidelberg, which is maybe known for physics. And then I decided to go into more environmental climate physics. I discovered oceanography and did my master's in ocean and climate physics in the University of Hamburg. And currently now I'm in Munich. I'm at the TU Munich. More exactly, I'm at the DGFI, which is the German Geodetic Research Institute of the Technical University of Munich. We do mostly geodesy, as the name says. So there's plenty of things done in the institute. The big topics, I would say, are on one hand reference frames, and on the other hand altimetry. That's how I can maybe put it in a very short way. And I'm in the altimetry group. And why am I here actually? This is because my PhD project, it's called Circulation from in-situ and Remote Sensing Data in Coastal and Shelf Ocean. I have to read it, it's very long. Short circus, and this is a project my supervisor came up with, and I'm the PhD student now, and it's also in collaboration with Martin Saraceno. So this is basically the main reason why I'm here, because in this project it's also focused on the Argentinian shelf, and this is the connection why I'm now here, because also my graduate school allowed me to go abroad, and I knew Martin. I mean, like the picture says, it's like 2022. We had lunch in Munich, and he visited us, so I know Martin since a while, and yeah, that's why I'm here. So blame him. Very short and sweet introduction to altimetry. I don't want to delve too much into technical stuff yet. So how do we measure sea level? Very easy. We send and receive the radar pulse from the satellite and measure the time it travels. We need for this the absolute, the very precise position of the satellite, of course, and we can, with this, derive sea surface height, which is like the altitude.
The orange one.
The orange one, yeah, okay. I think I'll stick, thank you. We can derive from it sea surface height. this is not very simplified. It's of course much more complicated. More complicated stuff is coming, so we also need to correct for plenty of things. So the signal might be biased by a lot of things, by upper atmosphere, for example, by ionospheric particles. So we have ionospheric correction. We have water vapor and density of the atmosphere, very easily said. So we correct for troposphere. We correct, for example, also for sea state bias. So if there's enormous wave heights, we have to correct for tides, because tides are one of a major ocean signal. And if we want to see something else than tides, we have to remove them. And also a very important correction for people that look at the ocean dynamics is the dynamic atmosphere correction. So here we correct for example, for the inverse barometer effect, so the pressure effect of the atmosphere on the water column. And then in the end, we get sea level anomalies from this corrected SSH. By just distracting the mean very easily. It's not that many easy. This is a figure. I think there's no presentation in altimetry without this figure. Prove me wrong. So this is very important. And we also know a lot of things from it. So one thing we see, so this is a history of altimeters, so of satellite missions that we have, and we learn two things from it. We have a very long, some decades, it's more than 30 years of measurements, and also we have an increasing number of missions. So we have, with an increasing number, increasing coverage of data, which is really nice. So here you also see there's plenty of designs of the satellites. There's also more, I didn't mention this, what I mentioned in the slide before is the very conventional radar altimetry, so there is more techniques, but this is like a very simplified view on it, and there's more techniques, more satellite designs. It's really worth maybe delving into this, but we're not doing it now. And altimetry is really nice because it has many applications. So of course, the first thing to talk about is the global mean sea level rise. We measure with altimetry. We can look into global ocean circulation by looking into the velocities that we can derive from sea level anomalies. We have bathymetry, so we have sea flow maps, really important. We have inland altimetry. This is from a study from a colleague from my institute. So they study river and lakes with altimetry. And we have ice sheet monitoring. It's also a very nice study. And we have thousands of things more. It's a really nice thing to maybe delve into studies from altimetry. So this must be motivation enough, I guess. And I go a bit more in the topic. So why we have gridded altimetry. So altimetry is usually along tracks. So if you have nadir altimetry, you see here the level 3 product. So there's level 1, 2. Things happens, and then we have level 3, the along track data. They are cross-calibrated along several missions, and still they are not very user-friendly. I mean, it's very maybe difficult and maybe also impossible to do a lot of studies with those kind of data. You have to imagine there are points, there's no data, there's missions have very different repeat cycles, very inhomogeneous. So this must be motivation enough to have level 4 data. They are handy, they are often in daily steps. You can use them, and they're necessary for a lot of things, especially when you think of spectral analysis, where you have to have gapless and continuous data. When you think of EOF analysis, or you want to see spatial patterns like eddies and currents, you have to have the continuous maps for this. So this is why gridded altimetry is the level 4 product. This is what users want to have. I mean, maybe not all users, but this is a very nice product to have in the end. And for this, we need some interpolation. So these maps are created through interpolation. This is two figures from a previous study. This is actually a first paper of me that I published also together with Martin Veracino, which is really nice. And we studied the state-of-the-art gridded altimetry, which is conventionally from, so at least what I know as the state-of-the-art, from Copernicus Marine Environment Monitoring Service. So I will now just say CMIMS instead, because it's very long. And we studied it in this paper. Also, we looked at the relation to wind. But what I want to show you here from these figures is two things. So here we see on the left figure, we see the coherence of the sea level anomalies with a model. So we looked at the GLORIS model and compared them over several years. And everything above 20 days is shown. So what we see is there's a really good agreement, except at the coast, especially at the southern coast. But what we also see when we look at the right plot, see the power spectral density, that the gridded altimetry, which are the solid lines, have a drop in energy towards small periods. So on high frequencies, the gridded altimetry is losing energy, and we see there is much more in the model, at least in the energy perspective, but that means also there is more signal and variability on the small scales, and the altimetry is losing it due to smoothing, due to filtering, and due to the gridding. So we have a lot of interpolation here. And what we wanted to ask ourselves is, can we improve the mapped sea level anomalies by only changing the gridding approach? So we're not changing data, we're not adding better data, no other retracking, no nothing. We take the same data and just change the approach. And what I want to show you is this mapping with spatial temporal window kriging, where we had a moving window of ±5 days around the target day. We take the along track data and we model the space-time dependency. And with this, we have created a data set in 2018 on the same grid size as the CIMA data, and tested it in 2 regions. So in California, because here we have a lot of tide gauges, and in the on the Southwestern Continental Shelf, Atlantic Shelf. Yes, and I tell you how we did this. So like I said, we collected the data in the window, and it looks on the shelf like this. What we did on the shelf is also we only selected the data on the shelf, which was, I think, a really important twist in the gridding, because we see some issues in the CMIMS data on the shelf, and this might be due to this rapid change of dynamics when we change from, change the bathymetry, change the whole ocean variability. Then we build a variogram. So this is now very basic kriging. Some that know kriging might be bored, some others might be a bit confused because this is now some equations, I don't know. So we built this experimental variogram by basically taking every pair of the observations and computing their semi-variogram, so basically their variance. And we plot, or we have done the variance of every data pair per distance in time and distance in space. And what we do with this, we fit like a model that's suited. So I found the summetric model to be fitting. So what it is, it's basically we fitted a combined space and time model where we have a variogram in space and a variogram in time. And then we have some parameter that is a joint variogram combining both, where we have alpha in there that is like a space-time anisotropy parameter that tells us how we convert time and space. To sum it up a bit, we model the time-space dependency on every day based on the data we get from in this window. And with this model, we feed the kriging system. So this is a ordinary kriging, very basic system where we in the end put all our data for every day and weight the observations. We get a kriging system of n+1 times n+1 matrix. So n is the observational data you have within this 11-day window. And what we have is, on the one hand, we have the semi-variance from all pairs of observations that we got. And on the other side, we have all the distances in time and space from every observation to the target point. And we feed it with the model. So we look at our unknown point and look at the semi-variance that the model gives us for every distance in time and space to every point. Yes, and with this, we got the lambdas, which are the weights we need to know how we can create now the weighted mean for one prediction. So those are all our predictions. Those are the weights we get out of this huge matrix. And this is then the predicted value for one grid point. It's a bit complicated. This was the prediction for one point at one day. And this is then to be repeated for each grid point. And the modeling of the variogram, this is then to be repeated on each day. So after we did all this complicated stuff, we have a grid which we can now validate. So we validated it against the CIMA-DCAO, against the model, which is the Glorious model. Yes, and then we also looked at the CIMA-DCAO and the model. So what we see is there's a very high correlation between the altimetry-based data sets. I mean, there's no surprise, they're both based on the same input data, but also we see slight differences. So at the coast, this is very small, but please trust me, there is some differences we can see at this map. You have a bit of increased root mean squared deviation on a bit of a decreased variance, so but it's higher variance of CIMA-DCAO. We also see that the OKST is the ordinary kriging, and CIMA-DCAO have a good correlation with the model, but both react with the model very similar. So we have not that much differences between both. There are a bit of a differences towards the coast. And because we cannot see the differences between CIMA-DCAO and ordinary kriging so much, we have to look at the numbers. So if we correlate the ordinary kriging with the model, we get the correlation which is slightly higher than when we correlate CIMA-DCAO with the model. So we're doing slightly better, very slightly, compared to the model. We can now look again into the energy perspective we saw before from the other paper. Something we can see here. So this is the mean power spectral density of the whole grid in California and on the shelf in Southwestern Continental Shelf. And we see that in blue, our grid has much more energy on all scales here than CIMA-DCAO in California. And on the Southwestern Shelf, we have more energy on the very small scales, and here there is higher energy on the CIMA-DCAO. So there must be some more signal or less signal. So we looked into something that we adapted from a study in Ballarota et al. They came up with the idea of defining effective spatial and temporal resolution for gridded altimetry. And what they did is basically defined the energy drop of 50% of the differences relative to independent observations to be the effective resolution. And we can do it in time and space. This is from their studies. So they co-locate the grid with an independent along track data, and along the distance, they compute PSDs. And the ratio of the arrow, very small, ratio of the arrow to the relation of the PSD of the along track data, of the independent data, can be plotted, and we find some distance in space here, which is then this effective resolution. And we can do the same in time by doing it against tide gauge data. And this is what we did. So we show the estimates for California because here we have enough tide gauge data. Here we have a homogeneous area that we gridded. So we used the 13 stations for defining this effective temporal resolution. And here we found a decrease in effective temporal resolution from 58 days to 34 days compared to the CIMA-DCAO grid. And we also did it in space. For this, we did the gridding again, excluding Zaral, Altica, and used them as independent along track data. We did this in 2019 because there was another grid from CIMA-DCAO doing the same, and we could use it for a fair comparison. And here we found no decrease in the effective spatial resolution. So we have the same, which also fits to the study of Ballarota. when we compare the grids now against the tide gauge stations, we can find that in California, we have 11 out of 13 stations that have higher or equal correlation. So we have the correlation here of the new grid, here of CIMAs against the tide gauges. So we could find an improvement in correlation, and also we could reduce the root mean square error. And the same, oh no, I should show some tide gauges. So this is how it looks like. So blue is the new grid. It's a bit more, it has a bit more variations. And see the orange grid. Model is very slightly seen in gray, and then the tide gauges. And then if we do the same in, I can show it later again, if you do the same on the shelf, we have 4 of 4 stations. They're higher or equal. There's one that's equal, and we have an improvement in correlation and reduction in root mean square error again. It's really nice. So here's also some examples for the tide gauges. Yeah, so for some reason, the model particularly was bad in model data. I don't know why, but the same correlation here, there's a quite good increase in correlation. Okay, something we also did is looked at the same analysis now with the tide gauges, but with a twist. So we're now looking at not the correlation, but the mean coherence, which is really nice because now we can maybe understand the correlation to the tide gauges better by looking at their correlation on the frequency scale. And we did this, I show it here as a mean over all those stations. So this is a mean over the 13 stations, and we see that the correlation or the coherence with the tide gauges is higher on almost every period or frequency than the tide gauges of the CIMAs. And we have the same here. So for every frequency higher than what is 15 days, we have much higher agreement of the new grid, tide gauges, which is nice. And yeah, some other perspective on this. Okay, so there is one particular example I also want to show. So there is the station of Puerto Madryn, and there was a particularly bad correlation of the Siemens grid. And if you look at the time series and at the map, we see that the orange line, which is the Siemens grid, has very high or low over and under estimations, which are not really fitting to the tide gauge. And if you plot it on the map, like this day here, and you see that there is really high, or if you choose another day, low blobs. So there's just some wrong sea level anomalies in this model, or not in this model, sorry, in this data set, which are not shown by our data, but it's a bit confusing at the beginning because we use the same input data, but somehow there might be outliers from maybe tidal models that are not completely correct in this region. It's a particularly difficult region, and they're somehow not catched by our interpolation. And this is a really nice example of how we could improve here the representation of the sea level anomalies by not having wrong data. I don't know. So okay, this was the study. Now you know it. This is a conclusion from the study. So it's a new original approach. Especially there's a breaking on the shelf with a short window might be good for a good representation. We found, yeah, our stations are better on the shelf here. There's more variability, more energy, and especially the reduction in this effective resolution is really nice on the temporal scales. And this is already a paper that I submitted with the co-authors, Marcello Passaro, my supervisor, and Denise Detmering. And it's in review now for advances in space research. So I hope you are super motivated to read it soon. I am. And there's also the data set. It's published on CIMA-DCAO for both regions. And I have the code on GitHub if somebody, I don't know, is interested. Always nice to share work. And now I just have some more comment on current developments and challenges. So to put it a bit into context, Also, of course, the hottest topic right now in altimetry is the new SWOT mission. And we have revolutionary good data now. So we have really high resolution snapshots every 21 days. And you see here the 10 days of Sentinel-6 and JSON-3 versus now the SWOT data in 10 days. And this very, very high resolutionary spatial data create basically a higher demand for better temporal resolution. So just as a little comment, maybe, this is how this looks. So we don't have the nadir only, but we have now very dense data here on the source. Also, there are other gridding approaches which might be, I don't know, more advanced or look into different directions. So we have many approaches use machine learning and neural networks. I posted here, like, of course, the own study of my supervisor where I could contribute. It's done with random forest regression, so something completely different than this. And neural network techniques are really coming or really new and really good. There's assimilations with a model for regional maps. And also, I'm a big fan of the synergy approaches. There's a nice paper I cited here for, they use neural network, but also they use dense SST maps for deriving SSH more precisely. Also very interesting. Just a comment maybe on what's interesting as well. And yeah, then I just have another slide on what I'm doing now here. So with this grid that I did, I want to study now the velocities. And this error bad values, this example that I had, you see when you derive now velocities, those things are getting even bigger. So it might be interesting to study how we can have maybe a better vision study representation of the velocities on the shelf. And then also I'm working right now with in-situ data in the San Matthias Gulf. I put it here like a comparison with the what. So just the thing that we saw before, there's now the very dense data. And I want to learn a bit on how use in-situ data that you have and work. Yeah, that's all I have for today. So I thank you very much for your attention and for having me.
Questions?
One.
Yeah.
In Spanish and in English.
You can, maybe you can come closer.
I will just do that.
People from Zoom can hear you.
No, I will speak in Spanish and then in English.
Okay.
Okay. La pregunta es si tenemos información de altimetría en ríos, ¿por qué nos sigue fallando cerca de la costa? Okay. Why, if we have now altimetry for rivers, there still fails near the coast? Did you know? You have some.
Wow, that's such a good question. You mean why there's still like not so good data on the coast? I mean, I think it's two things. So I think there's no like seamlessly combination, at least not that I know, correct me online people if I'm wrong, of those kind of data. And also coastal data are getting really better when we look at coastal altimetry, at the retracking of the coastal data. This is not included in this study for the reason that we want to be very comparable. I mean, we're comparing all the time to the conventional data. But to answer the whole question, I don't know for sure, and I'm afraid to give a wrong answer.
Okay, I will try to find the answer.
Yeah, but I can see if I can maybe answer this later a bit better.
Okay.
Yeah,
I can add a comment.
Yes.
I think it's something that people is really interested in trying to figure out why now we have two components with the same instrument. We have two components and they cannot match together. Not yet. They are trying to understand that.
Okay. Thanks, Laura.
Quick question. Why was it 2018? Why did you go to that?
yeah, good question. I think originally I was orientating myself a bit on the tide gauge data set because there was like this GASLA 3 tide gauge data set, and also there's like I think now 6 missions we use. So if you go later in time, there's additional missions, things take longer. And no particular reason, but honestly, it was because of the tide gauges at this time when we started. Yeah.
I have a question.
Ask.
When you explain the method for the new gridding, you mentioned that you are using a window of 5 days.
Yeah.
But do you have a window for spatially? Because I saw your figures with the variogram in time and space. I wonder if you also have a threshold in the spatial.
Yeah, so the way it's done is usually by you have this experimental variogram, and then from the variogram you would know what's the limit. So here, for example, you can see it on the spatial scale very nice. There's some saturation, so we see in space there is some limitation in the correlation, basically. But in time, we don't have the same. I mean, here it's a bit like this, but mostly not. So we cut the time, while in space, the range of the 200 kilometer comes from the variogram, by that we see that there the correlation is having a saturation. So it's not cut there on some purposes or thresholds, but more on how far does the variogram is. Doesn't make sense to fit it, basically, to fit it like a curve. Yeah, doesn't make sense. So it was a bit cryptic. Yeah.
You mentioned that you have like these two sites in California.
Yeah.
And there is a, if I'm not wrong, there is a big difference on the continental shelf that one has and the other doesn't. And do you think that can have like effect that having a lower what I call
on the validation? I think so. So we see much better results, or yeah, I mean, we see more increase in the quality on the shelf, and I think it has to do because we're cutting the shelf, and also because if we compare with the CIMAs, there are some particular errors maybe, but also if we only select the shelf data, we select some area that has common dynamics by its definition. So we know, I mean, I have no plot of it, but you can maybe imagine if you would look at the standard deviation of sea level anomalies, you could draw the bathymetry, you could draw the isobars. So by only having in the variogram represented all the shelf dynamics, cutting out this big confluence, this high dynamic that happens just off the shelf, we only model this kind of dynamic. So I think it makes a huge difference. Yeah, we could not do the same in California. The shelf is quite small. It would not be enough data. But I think this idea of using the same area of dynamic, if you cluster or if you choose it here on really on purpose because of the dynamics, is somehow key to getting a good dynamics represented. Yeah.
So you think these results that you finding at the dimensions are key could be found elsewhere in another continental shelf, or just this is very particular?
No, I think it could be found also somewhere else. So if you think, I mean, like I said, so there's on one hand, first you change the gridding, and by good luck or chance you have a better result. But then if you have this kind of clustering, this kind of semi-enclosed, enclosed basin, if you think of Mediterranean Sea, if you think of the European shelf, you could, I mean, I have no proof, but of course you can have same increase in results, I guess. So yes, why not? But it's only a hypothesis, so I can say you know everything.
You showed the story of the different missions, and
Yeah.
I guess that along that time there were also increases in resolution and technology, and I'm wondering what is the effect when you want to combine them. I mean, that increase does it get difficult to have changing missions in terms of resolution and other things?
Yeah, so
to compare and to mix the things.
I think there's two things. So if we look in the past, the really extreme you can have is like the 2 missions. So if you only have, and there's some study I did I tested this with only having two missions, so the JSON and Sentinel, because there's a complementary, like a similar thing in CMIM. So we have like this two-sub product, and it works. So we can still have a good grid, but if you do the exact same thing, you will have less variations, less variance, which is somehow reasonable, because if you have only two missions, you have much less data. So you have your one satellite, which is like every 11 days and one every 27 days. So if you do less satellites, you might enlarge the window you're putting data into. You might take plus minus 10 days. And then if we look in the future, there's what? So we have a large density of data. And this is a big question mark, because for so far, I only did this kind of thing with nadir. And of course, I also did a grid including nadir of SWOT, but how to include the swath altimetry, it's a question mark, because it's a really huge and dense data, but only on a very sparse temporal resolution. But yeah, for two satellites it works, but it would maybe need some tuning to really do it.
I just want to add something about what she said before SWOT. That's why all the time we were like before SWOT, after SWOT, because data goes along the track, and they compute the data basically that you have a singular point every, for example, 7 kilometers in case of one kind of altimeter, and every 300 meters in another satellite. But between the tracks, you have a dozen of more than 10 kilometers or 100 kilometers between the tracks. So when you combine all the satellites, you try to cover those gaps. And with SWOT, you have every 21 days, but every path has 150 kilometers with 1 kilometer of resolution. It's a pixel. You have like a picture of 1 kilometer, like a pixel with a pixel of 1 kilometer and width of 100 kilometers. So that's why it's like after and before and after SWOT.
Yeah, there's
suddenly in one snapshot we have spatial resolution that we haven't seen.
Yeah. Thank you. Yeah, it was just to show like how dense that was kind of data now. There's not like one stripe, but it's like. That's why I added it, because it's a new error.
Question.
Yes.
So, in the gridding, in the ordinary gridding method, you can consider that the measurements have an error that they do not. So I was wondering, the measurements that you use to derive interpolation, do they all have the same uncertainty in the measurements?
Yeah.
Because if they don't, if there's like heterogeneity in the uncertainty, maybe it'd be nice to do. It would be better to have a grading that includes the uncertainty.
Yeah, I totally agree. That's a really good point. I do the exact grading, because if you do have the not like not zero, it gets really unstable kind of. But it's a very, very good idea of putting the mission dependent or track dependent measurement point into it. It's a really good point, yeah. But I'm not doing it. So I'm putting the nugget to, it's an exact.
Okay, an exact interpolator.
Yeah, exactly. But it's a really good point.
But from when you started until now, do you think that it would be possible to with a grid product to improve the frequencies or energy between the 14 days and the 20 days that now the CMS is missing? Do you think?
That's really a good question. I mean, somehow at some point there is like an absolute limit. There's like so many points about this. So we show that we could increase the effective temporal resolution. So that's the facts now. But still, we have plenty of things. So we are limited. There is a limit because of the satellite constellation. We cannot interpolate something that is not there. I mean, we can get the best out of the data, but we cannot make it daily, like perfectly daily. And then also there's the corrections. So we have this correction I mentioned at the very beginning, this dynamic atmosphere correction. It has some cut at the 20 days, and we had also some discussion that also those kind of things have to be at the same quality and really good. So there are many things on the small scales that bias or kind of disturb or basically limit us towards the small scales. And somehow, I don't know, this is the honest answer, but there's many things to think. And I mean, fact is there is more energy at those scales, and we could somehow increase it. So we do not do the very much smoothing. I mean, if you looked at the tide gauges, we see that there is less smoothing, and I mean, there is variability and there is more, so there is more data and more variability on the scales, but 14 to 20 days, I don't know. Nothing.
Agradecemos de vuelta. Pero si no tienen otra pregunta, le agradecemos nuevamente a Marie. 2 semanas para el próximo coloquio.
So you will be around for a couple of more time?
Yes, I'm here since till April. I might not be around for some days, but I'm in 2301.
So it's good.
But also, if you want, so if you don't find me, I somewhere here. I have my email address. You can also write me or ask Laura to.
Yeah.
Okay.